Greetings from NITS-YantrarNav and welcome to the hardware functionality demonstration and progress update of Team NITS-YantrarNav rover representing NITS-YantrarNav at ISRO-Robotics Challenge 2024. Our journey so far has been filled with challenges, triumphs and invaluable learning experiences. Our team, comprising of 10 talented members from diverse engineering background, is driven by a common passion for robotics and innovation. We are proud to operate under IEEE Robotics and Automation Society NITS-YantrarNav subsection under the guidance of Dr. Taimur Khan and Dr. Koina Mukherjee. To ensure efficient workload distribution, we have divided our team into specialized subgroups, each focusing on key aspects of the project. As part of the mechanical engineering subgroups, we are responsible for designing and fabricating the rover chassis and manipulator arm. The electrical engineering subgroup is working tirelessly to develop the onboard control system and power management solution. In the software engineering subgroup, we are developing sophisticated algorithms to enable autonomous navigation and object manipulation.
Our team is fervently engaged in designing and constructing our autonomous rover that will navigate the simulated lunar terrain with precision and resilience. At the heart of our endeavor lies meticulous CAD design crafted using SolidWorks. Every component, from the chassis to the wheels, the robotic arm, and the rocker bogging mechanism, has been crafted to mate functionality with feasibility. Our chassis frame is constructed from lightweight yet durable aluminum extrusions. To ensure structural integrity, sheet metal brackets are strategically riveted at joints, providing both stability and flexibility. The wheels, crucial for maneuverability, features 3 sheet metal discs in parallel encased in hard rubber for enhanced traction. Mounted on the middle disc is a motor poised to propel our rover forward into the unknown expanse of the lunar surface. The robotic arm has 2 main links crafted from resilient sheet metal reinforced with 3D printed components for added strength and precision. The motion of the 2 links of the arm is controlled by linear actuators for strong holding capability. The arm will serve as our rover's tactile interface with its lunar surroundings, facilitating sample collection and scientific exploration.
For the fabrication of the autonomous rover, our mechanical team is currently emphasizing the utilization of locally available resources. Intensive CAD modeling along with mechanical and structural analysis is underway. We are strategically leveraging cheap aluminum extrusions sourced from the nearby supplier, supporting local industries while ensuring the Make in India initiative and cost effectiveness in our manufacturing process. To construct the rover's framework, we are currently using a combination of fabrication techniques including riveting, TIG welding and CNC laser cutting. Riveting is instrumental in securing joining components with the CNC laser cut joining brackets, while the TIG welding is providing strength and durability to critical structural elements. Sheet metal bending is currently enabling us to craft intricate robotic arm components along with the structural panels of the rover. Meanwhile, mechanical operations such as drilling and CNC milling are being performed at our department workshop to precisely shape and refine components, ensuring optimal functionality and performance. We are also integrating additive manufacturing, specifically 3D printing, into our fabrication process. By utilizing FDM 3D printing technology with PETG filament, we are rapidly prototyping and producing custom components for the rover and the robotic manipulator arm, such as the bevel gear and mounts, reducing lead time and promoting local additive manufacturing facilities. Our project's emphasis on sourcing material and service locally is currently having a positive impact on nearby industry.
Hello everyone. So in this section, we'll talk about the electronics that we're going to use in the rover. The main heart of the electronics, that is the Arduino Uno, which is used for controlling all the robotic wheels and the robotic arm, is the main heart of the electronics and will control using the PWM pins of the Arduino. The Arduino is tested for controlling the 6 motors using the Smart ELX motor drivers that we're going to use for this purpose. The Smart ELX motor driver has a max current rating of 15 ampere and will efficiently drive the motors of the wheels. Next up, we have the servo sheet that we're going to use for controlling the servos. The servos are used for the Ackermann steering mechanism and the robotic arm. Next, the servos that we're going to use for the robotic arm is the RD-S3115MG servos. These servos has an efficient capacity of high torque and high efficiency with a continuous voltage range of 12 volt and a max current of 5.6 ampere. The stepper motors are also used for the robotic arm controlling. The stepper motors will be efficient for controlling the rover's arm and give a high torque capacity and high uplift capacity for the robotic arm. For the robotic arm, we are also going to use the linear actuators. This linear actuator has operating voltage range of 12 volt and current rating of 2 ampere. This is the motor that we are going to use for the robotic wheel. The motors have a high torque capacity of 800 Newton per centimeter and an input voltage range of 12 volt. The power converter that we're going to use is the Narco 5 ampere power converter, which will step down the voltage from 12 volt to 5 volt for the efficient controlling of the servos. And the next power converters that we're going to use is the RoboWave DC to DC power converter that will have a maximum current rating of 25 ampere and will step down the voltage from initial 24 volt to 12 volt. The main power source is a 24 volt 30,000 mAh battery which has to be efficiently distributed using a power distribution system which is made using a PCB and buses. The buses will efficiently traverse parallelly through all the driver motors, and the remaining power supply lines will be controlled by the robotic arm. The robotic arm will have an efficient voltage range of 12 volt to 5 volt in which it have to operate, and the motor wheels have to operate within a range of 24 volt to 12 volt. So it have to be stepped down to 12 volt and efficiently controlled by the motors. So the microcontrollers and microprocessors that we are going to use for these purposes are the Arduino Uno will serve as the main electronics for controlling the drivers, and the ESP32, a second microcontroller that is used for wirelessly communicating with the rover. The main mother microprocessor is the Jetson Nano processor. For communication between the Jetson Nano processor and the Arduino Uno, we are using a universal asynchronous receiver transmitter protocol, that is a UART protocol, for communicating with the Arduino Uno and Jetson Nano. The Jetson Nano will pass on signals to the Arduino Uno for autonomous navigation. In case of failure of autonomous navigation, the bot will be controlled using wireless communication using the ESP32 chip, which works on both Wi-Fi and Bluetooth. For this rover controlling, we are using the Wi-Fi.
The Jetson Orin Nano serves as the brain of our rover. All computations, including path planning, object and crater detection, will be performed by the Jetson Orin Nano. Our rover will calculate odometry by fusing wheel encoder data and data received through an IMU by passing them through an extended Kalman filter. We are performing SLAM using an RGBD camera. This camera will also be used for object detection. We will also be generating a 2D map of the arena by using a LiDAR for redundancy, as the RGBD camera may be affected by extreme lighting conditions.
Our software team has been hard at work developing cutting-edge algorithms to ensure our rover can navigate the lunar terrain autonomously. Using advanced image processing techniques, our rover would analyze the terrain in real time, identifying the obstacles and determining the safest path forward. Our object detection system utilizes deep learning models like YOLO V8 and VGG, trained on thousands of images to accurately identify craters and objects to be picked up for the mission. By integrating these object detection algorithms, our rover would be capable to make split-second decisions to avoid obstacles and to continue its mission safely. We are also using 2.4 GHz and 5 GHz dual-band antenna for transmitting our data to the base station and communicating with the rover. One of the key features of our software is its adaptability. We have designed it to be easily customizable, allowing us to tweak its parameters and algorithms to suit different environments and challenges. Whether it's rocky terrain, steep inclines, or unexpected obstacles, our rover is equipped with IMU to handle whatever challenges the lunar landscape throws its way.
Despite the challenges, our team's dedication and expertise continue to drive us forward. With each passing day, we're inching closer to our goal of delivering a cutting-edge robotic solution for the ISRO Robotic Challenge. Thank you.